Great. Thanks, Zach. Yeah, I'm Suraj, excited to be here, and thanks for having me and giving me the chance to talk a bit about what we're doing at Physical Intelligence. Um, so at Pi, our goal as a company is really to build towards a future where we have truly general purpose robots, right? So what does that mean? That means we want a robot that we can just, drop into a home it's never been in before, and have it do, useful, dexterous tasks for us, like telling it to clean up the kitchen, being able to command it in language like Chelsea is here, and tell it to do various parts of cleaning up a home, right? And to have it truly be a generalist, right? That so even if it's a home it hasn't been in before, even if it's a task that it hasn't exactly seen before, to be able to do this effectively the way people can. And so, what's been missing in accomplishing this goal? I mean, I think there's a number of pieces, but certainly one part that, for a while we've had hardware that's been capable of doing some very impressive things, right? So like given given scripted motions, we can have hardware do some really dynamic, really impressive sorts of tasks for a while. And at the same time, we've also seen robots, deliver value for many years in these sort of constrained industrial settings, right? So it's a very, very seen environment. You know exactly where the object's going to be. And in those settings, robots have been doing some pretty useful things and delivering a lot of value for a while. So it feels like, really where things start to break down is when we're trying to bring robots into the real world, into places where they truly need to generalize, right? Where you need to see, handle unseen objects, unseen tasks, unseen environments. That's where things have been a struggle. And it's really been this kind of core lack of intelligence. Um, right. And that's very different to the way, humans operate, right? So humans are actually fundamentally generalists, right? So for example, I can play some basketball. um, I'm able to do some cooking and use tools like a knife to cut items. Can use other tools to control other machines, like typing on a keyboard or driving a car, right? So if you look at actual humans, we're all sort of generalists. We're able to do lots of different tasks with lots of different objects in many places, right? I can cut a cucumber in my home or yours. And then you also still see specialization where, I obviously can't play basketball like Steph Curry. And so different people are basically generalists that then can specialize and be really good at certain things. Right. Um, and the closest sort of analogy that we've seen in AI systems has just been in this kind of growth of foundation models has really taken off in recent years, right? So language models, vision language models have gone really good, kind of built on this recipe of a generalist base and some specialist training on top of it, right? So we see that like the various foundation models, basically every benchmark that is set, is quickly and even more quickly being solved. We see that the length of like continuous tasks that AI systems can do is getting longer and longer, right? And then AI systems are also able to do these really challenging tasks, like kind of like superhuman level things in math and encoding and the like, and also can basically just generate any image you can think of, or any sort of video you can think of, right? So kind of the core recipe here is this idea of large scale diverse data being consumed by a powerful model that gives you a really strong generalist base that can then be specialized in various ways to do useful tasks. And so really what we want then is the sort of equivalent for robotics, right? What is this sort of generalist robot brain? It doesn't need to be the case that, it's exactly the same robot doing every task, right? So really what we want is something where it gives you this foundation that's sufficiently general that you can then plug into whatever's the right robot for a task, for that particular scene, and either be fine-tuned or zero shot can do that effectively. Right. So we want a model that can control any robot to do any task in any place. Now, I think this is, we're certainly not here yet, and this is kind of a vision that the field has been pushing forward for a while. But I think in the last few years, there have been a number of signs that, something like this is promising, and there may be signs that this type of recipe that we've seen work in language models and vision language models could be effective in robotics. Right. So I think one of the first things that we saw a few years ago was this idea that, these highly dexterous behaviors of robots really doing fine-grained tasks could be learned with just end-to-end, deep networks. And I think for a while, this was not clear, right? It was not clear that, something really precise didn't need some much more, advanced controller or some heuristics baked into it to be able to do these really dexterous tasks. And it turns out that actually, very dexterous behaviors can be learned with end-to-end learning. So I think this was one really exciting moment in 2023. The other, I'd say, big breakthrough that gave some hope that this could be accomplished is that robotic foundation models could actually build on on the shoulders of language models and vision language models, right? And so some of the early work on RT2 showed that, something like you could take a VLM that has all this sort of general knowledge about in an image, this is what a strawberry is, this is the flag of Germany, and actually inherit that knowledge and still use it as a sort of end-to-end control policy, but retain some of that general vision language knowledge. And then the third bit is that this idea that you can actually just pool all these data from different embodiments together, right? And so this is towards that goal of like one model that can work for any robot and whatever the right robot is for that task. I think some of the first glimmers that something like this could be done is around OpenX effort, where you had one model that could control, a lot of different embodiments, just consume data from a lot of embodiments and control many out of the box. Yeah. So some of these ideas kind of really inspired one of the first things we wanted to build at Physical Intelligence when we started about a year and a half ago, which was kind of bringing some of these ideas together and really building our first attempt at a robotic foundation model. So this was Pi Zero, right? And it has a lot of the pieces of kind of what I just described, right? So it's actually going to start its life as a Polygemma VLM, right? That's trained on images and text, to answer all sorts of VQA tasks, and have some general knowledge of vision and language. There's going to be a still end-to-end, network that's kind of added on. That's this action expert that's going to use flow matching to actually generate continuous actions to do these dexterous tasks on robot. And then we're also going to basically build up a pretty diverse data set that's going to have a lot of embodiments doing a lot of tasks. In some scenes in Pi Zero is a relatively smaller amount of scenes, but just sort of this first attempt at a cross-embodiment, cross-task data set. Yep. And this is what we're going to train Pi Zero on. So to put things into perspective a little bit about this data, at the time, the largest sort of prior real robot teleoperated data set was the OpenX effort. You were looking at about 3.8 K hours. And so, by the time we had released Pi Zero, which was maybe 6 months into the company or so, we'd collected kind of a bit over 10,000 hours of this sort of internal data set that's covering, on the order of maybe tens of environments or scenes, but hundreds of tasks on, over a dozen different robots. So this was kind of that first data mix. Now, once you've trained Pi Zero on this data, there's a few different things we can do with it. And the first thing is we want that ability to just zero-shot control of different robots doing different tasks, right? If it's data that you've seen in that pre-training mix, across different robots, you should be able to do it. And so the first thing we looked at here was just our ability to do zero-shot control on many embodiments. So here we have tasks on like a single arm UR5, ARCS robots, Trosson robots, right? And so these are tasks like bussing the table, shirt folding, taking toast out of a toaster, right? So these are all seen in the pre-training mix. And this is basically just measuring how well does the pre-trained model fit these and then is able to do them zero-shot. And we can see we're able to do, this pretty effectively and cover a lot of tasks or several tasks on several robots without any added fine tuning. And a couple of things I'd point out here is one of the more interesting bits is that we also compared this to Pi Zero Small, which is basically an identical version of Pi Zero that is not using the VLM pre-training though. And so this is just a independently from scratch trained transformer model with the flow matching head. And that's quite a bit worse. So I think this gave some more evidence to this idea that, okay, we can actually inherit something from the vision language pre-training that can make these VLAs more robust. Yeah. So that's zero shot control. But the other thing we wanted, so that's sort of our generalist base. But we also then, was there a question? Did somebody have a question?
Not in the room.
Oh, okay. All right. Um, cool. So yeah, so that was sort of zero shot, right? We're looking at that sort of generalist base, the ability to just do tasks out of the box. But like I was saying earlier, from that generalist base, really where these AI systems can get very powerful is when you can then post-train them to do really difficult tasks effectively. Right. And so we also had this effort of then taking Pi Zero and fine-tuning it to doing, various challenging tasks and dexterous tasks, both some ones that were still in the pre-training mix, but getting them to be a lot better, and also some that are unseen in the pre-training mix. Okay. So here we can show, there's a few videos of these tasks. So for example, on the top left, we have this like box building task, and this is one where this is not
Um,
seen.
Actually,
Yeah.
we just had a question from Zoom. I think one of the audience members was interested in the differences between Pi Zero and Pi Zero Small, if there are any architectural changes, or if it is just just the weights aren't from a pre-trained model.
There are architectural changes as well. So it's a smaller, like about 300 million parameter from scratch model that still uses like some pre-trained image embeddings, but it's a smaller transformer that
Mhm.
and then the action head. So it's smaller and it's also not a pre-trained VLM.
Okay. Awesome.
Yep. Cool. So we can see here some of the tasks that we fine-tuned to. So for example, in the top left, this is one that's unseen in pre-training. And then we're able to fine-tune a policy to do it. And then we've also had a few other tasks here, like the ones on the bottom. Let me just make sure these are playing. Where these are tasks that, in pre-training, there's some data of this task, but it's varied. And then at post-training, we will basically post-train to like a smaller, high quality mix and try and get these to work and be much more performant. But generally, we did see that we can then take this generalist space and fine-tune it to do more dexterous tasks. Cool. So that's the general recipe here with Pi Zero. Now there's I think we have a question in the room. No? Okay. Um, so like I said, in Pi Zero, we basically had this VLM backbone where we then had this flow matching action expert. Right. And so this is going to basically denoise from noise to continuous action, so action chunk. That's what's going to be played out on the robot. But there's actually some downsides of this. And I think kind of the core one is that this is not this is actually quite different to how the VLM is pre-trained, right? And so I think you end up with training this way with just some non-ideal learning dynamics where one, it takes a really long time, right? So you can see on the plot on the right, basically you're looking at like over a million training steps for performance to converge. And in general, because it's so different from the VLM pre-training, I think you actually lose a lot of the information that the VLM had internally because this is something that's pre-trained with next token prediction, and then suddenly you're just bolting this diffusion head on there and passing gradients in. So we wanted to see if we could actually make this better, right? So like one thing you might out of the box think you could do is maybe we just take our actions and discretize them and then just autoregressively predict them, right? And this is something that has been done before and works like RT2 and the like. But one of the challenges here comes when you actually try and combine this with action chunking, right? So you often end up with a chunk that has a lot of repeated tokens, right? So like, you may end up basically predicting the next token along this action dim for many future steps. And in practice, we found that this actually makes this quite a lot harder to train, right? Because you have these repetitive tokens, it's very easy for them all to just learn to predict the identical token on the next step. When you combine this sort of like just naive discretization, chunking, and autoregressive prediction. And so this was kind of our motivation to think more about, is there a way we could actually do sort of discrete token prediction, but in a way that's more amenable to training? And so we're looking at basically how can we actually compress the actions here, right? And we were motivated by some of the compression techniques used, for example, in like JPEG compression, right? So where basically you'll take some sensor stream, or it could be a 2D stream like an image, and you're going to represent it as like a sum of cosines, right? So you basically have cosines for the different frequency bins and a weight per each. And then depending on how many of those bins you keep around, you can basically get a higher and higher quality reconstruction at the cost of less compression, right? So this is basically the discrete cosine transform. And what we did in the FAST paper is we basically applied this to action chunks, right? So you're going to start with your normal action chunk. This is like, 1 second's worth of action. So let's say at 50 hertz, it's like a sequence of 50 actions for, some number of dims, whatever the action dim of your robot is. And for each dim, so this is basically a sequence. And you can basically just use the discrete cosine transform to map this into frequency bins and associated weights on them. Now, once you've done that, that actually has not immediately it has not saved you anything, right? Because but you actually need to then quantize and then just use and basically byte pair encode to get the compression, right? So what we're going to do is like once you've represented your action dim in frequency space, right? You're going to quantize them, and basically this is going to amount to just like dropping all the unrepresented frequencies to zero. And then when you order this, you're going to basically make this a sequence where you have like for each frequency, you have the weight starting with the lowest frequency ones, and that's going to be your basically sequence of tokens, right? So that's basically where most of the information is going to be in those lower frequency bins, and so it's it could be the case that basically with just the first 10% of bins that you're covering, most of what you need to represent an action, right? So that's the compression part. And then you're going to byte pair encode this. So you're just going to treat this as a sequence. So this byte pair encoding is going to map this sequence of like frequency bins and weights to a set of like 10, 24 action tokens. Okay. And then these tokens are now what are going to be what the VLA predicts. Okay. And so, yeah. Yeah. Do you have a question? Nope. Okay. So there's like and there's a kind of simple didactic example you could think of, right, where you can show that, for something like just interpolating a simple cosine wave, as you really scale up the fine grainness of the frequency bins, naively discretizing will get to be really bad, but something like the DCT will be really nice to predict, right? Because it's always going to have all that information in just like the first few bins. Cool. So going back to the original Pi Zero architecture, right? If you recall, we had this had taken over 1 million steps to get to good performance. If instead of having that action expert head, we instead just predict these DCT actions, we can get much faster training, right? So basically, you can match the performance of like over 1 million steps of like the Pi Zero training within like just over a few hundred 100K, 160K or something like that. Cool. So this is great. Now, are there any downsides? Well, there still is a downside, and that comes at inference time, right? So even though the DCT gave us really good training signal, a good gradient signal during training, fast training, at inference time, you still are then auto-aggressively predicting even the DCT tokens. And this is slower just because you have to predict it auto-aggressively than if you were to, use that action expert and diffuse out, the whole chunk in one go. Right. So the downside here is you get better training, but you have worse and slower inference. Now, one thing you could consider doing is just doing both, right? And keep the DCT training around as a sort of as a training signal, but then you also have the action expert that you can then use at inference. And generally, I think this is not a bad recipe, but we did find that this actually plateaus performance earlier, just because generally, again, the gradients you're getting out of the action expert, I think, tend to not actually be good for the VLM, right? Because of just how different they are. So the idea in the knowledge installation work, which was led by Danny Dries, is to do this recipe, but to also introduce a stop grad, basically. So you're going to co-train, you're going to co-train with the DCT discrete action prediction. You're still going to have your action expert that's using flow matching and predicting continuous actions. You'll train them together, but now you're going to not pass any gradients from the action expert back into the VLM. Okay. And performance-wise, we hope this can kind of be the best of both worlds, right? Because at training time, you get the faster training from using the DCT tokens, but you also kind of keep the knowledge in that VLM protected, and then at the same time, you still get fast inference, right? So the inference time can be as good as the normal Pi zero flow matching is. Okay. Cool. So you don't want to be slow like autoregressive VLAs, but you or but you want to keep the fast inference, but the better performance. Cool. Did I hear a question from?
I've got one. Can you help us understand the amount of compute and energy resource required to run Pi Zero? Are we talking like I need a desktop class GPU or a server class GPU, or can I run it on a Jetson? What does this look like?
For inference, right?
Yeah, yeah,
Yeah.
for inference.
Yeah, you can so these numbers I believe are all benchmarked on a 4090. Which is a consumer grade GPU that you can buy. And yeah, as for smaller systems like Jetson, we have not. It's possible we actually have benchmark performance on that. I don't know off the top of my head. What I would actually check is, and I'll mention OpenPy a bit later, but we've open sourced these models and has provided some code to run inference with them. And on the GitHub, you can find probably some specs about inference time on different pieces of hardware. But I think the standard one is like a 4090. You can definitely run reasonable inference. And I'm pretty sure these numbers are with 4090.
Thanks.
Mhm. Cool. Any other questions here before I move on anything I've talked about? Cool. Okay. Great. So just looking at the sort of quantitative numbers here, right here we're comparing the performance of the knowledge installation approach versus joint training versus Pi zero or Pi zero fast directly. And in general, we get, because the policies are able to actually run faster in real time and retain the good training dynamics, they generally performs quite well. Freezing the VLM backbone we find actually works quite poorly. And then this is a similar plot on time to completion. So here lower is better. Okay. Cool. So up to this point, I guess what have we covered, right? So I think the big takeaway from Pi zero is that, hey, we can actually take a pre-trained VLM, we can add this flow matching head and use it to get sort of a reasonably good starting point of a VLA that's able to be fine-tuned to do dexterous tasks, but can also run zero shot on a lot of embodiments. And then with fast, we were able to train these a lot faster with the sort of discrete compressed action chunks. And then knowledge installation kind of gave us the best of both worlds, where we could keep the fast prediction during training and then use faster flow matching at inference. Okay. But so that's all cool. But everything I've talked about so far has been restricted to the sort of space of environments we collected data, right? So, this video, all the videos have shown up to this point, these are places where you have data of that task in that scene that you're training on. And going back to what I talked about earlier, really what we care, most about is this idea of a generalist, something that you can actually drop into the world and have it do useful things. Even if it's a place it hasn't been before, or data hasn't seen data from exactly that setting, right? So that's what, after Pi zero, really the thing we started thinking most about was this question of how do we go outside of the lab, right? So the real world is really messy, it's diverse. This is a picture of my kitchen. There's a bicycle in it. There's like all sorts of random stuff all over the place. It doesn't look exactly like any other kitchen, right? And so for a robot to be useful in these sorts of places, it really needs to be able to handle the unknown, right? Unknown objects, unknown environments. It can't be the case that you drop it in here and it's just like totally clueless and doesn't know what to do because it's never seen Reese's Puff cereal or something like that before. Right. So based on this, we set our goal for Pi oh 05 to have a robot clean a totally new kitchen or bedroom zero shot. Right. So there's a number of reasons why this is hard, and probably if anybody in the audience has worked on, training policies and pushing them to generalize, uh, you can appreciate why it's hard for a number of reasons, right? And I think the first one that I would emphasize that I actually think is maybe at the core of it is that, fundamentally new scenes and objects will require different low-level control, right? So like the the videos we have here on the right are of us, seemingly simple tasks in isolation. They're all one task, which is like opening the cabinet, right? And it's like not a particular long horizon task by itself. But what we can see here is that like in these four different environments, you actually end up with, opening the cabinet actually ends up requiring like a fundamentally different low level control and how you grasp the knob. Maybe there isn't a knob that you can grasp and you need to hook your finger underneath the cabinet like you see on the bottom right, right? Or you need to like pinch some little piece of metal that's sticking out, right? So like the low level control really changes depending on the scene. And I think that's really the core of what makes this like really hard for the low level policy to generalize in this way. And there's a similar story also for a high level understanding, right? So like, if you're in a kitchen and the task is okay, you need to put away the dishes. That means you actually need to understand what a sink is, uh, and where it is in this context and how to navigate there, right? Even if the layout of the kitchen is something you haven't seen before, even if the sink itself looks different from any sink you might have seen before, you need to be able to recognize that is a sink. This is how you need to get there, right? So both at the low level control and at the high level reasoning, there's like each environment can afford basically a totally new way of doing the task. So that's really what kind of, I guess, inspired how we think about the data we need to collect for this, right? Um, and I think the first natural choice is like towards tackling that first point, right? Of like in different scenes, what is the right low level control you need? This is where we basically scaled up our teleoperated data collection in many different environments, right? So we basically took robots to homes all throughout San Francisco, and went in there and collected a pretty diverse set of tasks in each home, and then each home naturally afforded those sorts of axes of diversity that we're thinking about, right? We saw tons of different microwaves that need to be opened in different ways and need different low-level control to open them, right? So this is just like our mobile data, multi-environment data, right? So actually, like the reason, and another point here is the mobile part of this, right? Is one of the reasons we chose to structure a lot of this data as mobile is just fundamentally to do a lot of interesting tasks in a home. I think you need to be able to move around, right? Homes are designed for people. The number of tasks and space of useful things you can do in a home is just so much greater with mobile robots. So that's why really like the core push of ours was taking mobile robots into a lot of homes, teleoperate them to do a lot of different tasks, right? So that's the first piece of it. At the same time, there's also some downsides of mobile robots, largely that they are, bigger, harder to move around. I think in general, the teleop interfaces on them are still sort of open area research. So in addition, we kind of brought on these like static clip-on robots, which are really quite nice, right? Because it's like small box, you can just clip it onto any counter, take it to all these different homes, and again, collect more teleoperated data of various diverse tasks interacting with diverse objects. Okay. So these are both teleop and then and done in multiple diverse environments. The other bit of data we thought to use was web data, right? And so this is really what's getting towards that high level reasoning bit of like, what is the sink? How do I navigate there in a totally new kitchen? Right. So web data has that sort of internet scale knowledge of like, here's, thousands of sinks and what they all look like. And so we added sort of web data in the mix. And then the last bit of data we trained on for Pi oh 05 was we still kept that Pi 0 mix I talked about before. So this is still largely in-lab data, but it's a lot of embodiments doing a lot of tasks, right? And so you still just cover a good amount of sort of task and object diversity in this data, and there's a lot of it, on the order of well over 10,000 hours. So we're going to include that too. So this is the data mix for Pi oh 05. Right? So put in a perspective, at Pi Zero, we had these, 10K hours of internal data, but it was just in tens of environments. Um, by the time we got to Pi 05, we had many more than 10K hours of static data, but we then also collected 400 hours of mobile data across all these diverse environments. And so one thing to note here is actually like the quantity is actually not that much, right? For like compared to the tens of thousands of hours of static data had at the time of Pi 05, we just collected 400 hours of this mobile data, but there's a much bigger emphasis on diversity, right? So it's about diversity much more so than about quantity with the multi-environment data. I think I saw a bubble pop up from the chat, so maybe I'll pause if there's a question.
Yeah, we just got an audience question. Question is, do you see an active perception behavior emergent from this large data? We want to understand the question correctly. Favor the policies, right? You see kind of emergent behavior where the policy needs to orient its camera to observe, the right a knob, for example, if it's opening a cabinet, or get views on target that facilitates the downstream tasks.
Yeah.
That.
Yeah, it's a good question. I would say that type of emergent, I mean, again, it depends how we, what classifies as emergent here. For example, it might be the case that like, for example, if teleoperation data was collected where, the left gripper looks at the item closely while the right gripper does something, the policies can do that. And this is still all very much in the sort of supervised learning setting. So if it's there in the data, it's there, but I don't know if I would call that emergent. I think where you might see more of that is again like this idea of like you need to look around to find something, right? Like you need to search before you can know where an object is, to know what to do, and that's that sort of active perception. One thing I'll say is I think so none of the models I'm talking about today have frame history. So these are all single time step, meaning that the input to the model is like this time steps all three cameras or four cameras, right? But there's not a history of observations, and I think that is it's an important problem. It's something we're thinking about, and I think that's probably a prerequisite to this sort of like active perception working, is that your model actually needs the capacity and the ability to ingest that data and use it. So I wouldn't say we've observed that yet.
Yeah. Awesome. Thank you.
Cool. So what is the model we trained on Pi 05? I'll keep this quick because it's very similar, I think, to what I presented earlier. Actually, the difference being that this was before the knowledge installation work was done. So during was there another question?
No. Oh, just thanking you for your answer.
Oh, cool. So for in the knowledge installation work, recall that we basically co-trained the with the DCT loss and the action expert, but with the stop grad. Actually, at the time of Pi 05, we did a little bit differently. So at the time of Pi 05, actually during pre-training, we were only using the DCT loss, the fast loss, but then adding the action expert for fine-tuning. So at Pi 05 pre-training, basically we pre-train with robot data where we're predicting, the discrete fast action tokens, but we also had like other auxiliary tasks like bounding box prediction and language prediction, like what's the next subtask. That's all on robot data. So that's just like lower bullet point here. And then we also trained on that web data that I described, right? So we're using like BQA data, image captioning, bounding box prediction. There's a list of like something like a dozen data sets that if you check the paper, you can see the list, but we include all of these, right? So you can see some examples of different tasks that are included at pre-training here on the right. So some of them will be like localize the gripper. Some of them will be like predict the actual discrete action tokens for picking up the pillow. And some of them will be like, given clean the kitchen, what's the next thing you need to do? Okay, it's like putting the plate in the sink. Yeah, so that's pre-training. And then at post-training time, it's pretty similar, except now we're also going to add in the action expert again, and this is just going to produce the continuous actions. And we're also going to keep around this like high-level task of subtask prediction, which is like give and clean the bedroom, predict that the next task is pick up the pillow. And so the reason this is relevant, right, is because these mobile tasks like clean up the kitchen or clean up the bedroom are very long horizon, and actually it helps a lot to break it down hierarchically, right? So in Pi 05, we had this hierarchical approach where first, given all the images in and the high level sort of prompt, like clean the bedroom, the model is first going to actually predict the next language subtask. So like in this case, it'll be pick up the pillow, right? So that's sort of your high level policy. And then that's going to then be an input to the low level policy, which then generates the low level actions. So then when you're running inference, it'll be something like maybe every second or two, you run high level inference and generate like, okay, the next subtask is, move to the bed. And the next one is like, pick up the pillow. And then the low level policy will constantly be consuming these and outputting control actions. Okay, so that's the model setup and inference setup for Pio 5. Let me just pause briefly if there's any questions on that. Cool.
There is one question that just came in to the chat. Do you see next improvements most likely to come from better context accumulation in the pre-trained autoaggressive backbone, or from better use of the action expert? For example, using diffusion, forcing, or another way to condition on short horizon history.
I see. Oh, so this is really focused. It sounds like this is focused on the history part. And if I'm understanding correctly, is asking like, do I expect to see more benefit from like baking it into like what goes into the BLM versus using something about diffusion and to like account for history? Am I understanding that right?
I believe so. I believe perhaps it's looking at the bottleneck. So yes, yes. It says that's
Yeah.
the
Okay, great. Yeah, I mean, I think I think it is both, right? Because I think there are some things where you really need like true image history, and ways of getting that into the VLM are
Mhm.
like, yeah, I don't think there's any way around that, right? Like there are going to be tasks where without like a history of images, you just don't know like where the object is that you need to pick up or something, right? So I think
Mhm.
that part is important, but I do think there is stuff you can do um at the lower level action, at least for like, yeah, continuity and smoothness of action, right? So like one of the papers, I'll briefly mention it later too, but one of the follow-up works that was led by Kevin Black here was on real-time action chunking, right? And the idea being that like you can run the low policy asynchronously and then blend and actually, use a guidance term to blend it properly with the previous action chunk. And in a way that's history, right? Because you're saying my next action chunk, I'm going to make sure that I generate it to be like somewhat consistent with the last one. So
Mhm.
it's true that you can also do that at the sort of inference like diffusion level too. And I think probably both are necessary.
Mhm.
Cool.
Awesome. Yeah, thank you.
Cool. So here's just a video of what that sort of combined high level, low level inference looks like. So, Laura just said here, clean the bedroom. And then as it's going through, the high level is saying like pick up the trash, put it in the bin, move to the bed, pick up the pillow, and the low level is acting on it. Cool. Sweet. So I'll briefly talk about the sort of quantitative experiments we was that a question? No. Okay, I'll move on. So yeah, I'll briefly go through the quantitative experiments here. So here we picked 4 tasks, and we really want to understand basically the design decisions in Pio 5. And so we tested them in a bunch of both real and sort of mock home environments. And I think kind of the headline plot that is most interesting is, really we want to understand like how are we generalizing given different amounts of environment diversity in our training data, right? So the x-axis here is like the number of locations of scenes where we've seen data from, and then the y-axis is the performance in a unseen set of environments. And what's pretty cool is that actually after only 100 environments, we're getting similar performance in this like unseen scene as if we had collected data in that scene. So that's what the green bar is. Which to me was really surprising. Like I think this is a question I think like we had wondered about for a really long time. And going in, I think people didn't know, depending on how much you can inherit from the VLM, like what is it? Is it like order 10, 100, 1,000, 10,000 environments? And so it was really interesting and cool to see that actually only about 100 environments was enough to match that performance. But one really important bit is that general pre-training was necessary to do this, right? So if you didn't do the pre-training phase and you just did the post-training phase, but with the same diverse environment data, it doesn't work, right? So when you drop when you drop pre-training, the scene performance is halved, right? So that's like the two green ones, but the generalization performance is basically non-existent. And this was super interesting. Now, I think, is it going to be the case that for every task, 100 environments is enough? That's not necessarily the claim. Like, I think, you know, it, it, this was what it was for the 4 tasks we tested on. And things may also look different when you need to match when the in-domain performance is closer to 100. How much does that basically mean you need a scale number of locations to get the generalization performance to also be 100? So I think, I wouldn't say it's like done, oh, 100 is the number that you need to generalize necessarily. But in this case, it ended up being kind of less than we expected. But there's definitely still a lot more room to explore here. We also looked at basically how these different data types we talked about actually impacted performance. And kind of getting to the earlier point about pre-training, including that static data, just because it's so easy to go around and cover a lot of spaces, and also including even though it's not environment diverse, but it's like task and object diverse, that cross-embodiment data from the lab, both of those ended up being quite important. And so if you don't include those in the pre-training, you get a dip in performance. Um, in the standard set of tasks, there's like a little bit of a lift from the web data, but I think really where we saw it help the most was in this sort of OOD robustness, right? So here we're giving it like, picking up all sorts of weird objects and like follow language to pick up the right weird object that's like, the goggles or like the guitar shaped spoon. And this is where you see like the web data making more of a difference. Yep. Cool. And then, so we didn't just test this in one home. We took it to a lot of different homes and tested the zero-shot performance. You can check out the website and see a lot more videos of this. But this was pretty exciting for at least me personally. I think this was like one of the first times we saw that, okay, you could take one of these dexterous VLAs, scale up diversity of data in the real world, and along that axis in which you scale data, see some meaningful generalization. Yeah. Cool. So Pi 5 and Pi 0, but Pi 5 is probably the one we're trying. So we've open sourced these. And so you should check out OpenPy, a lot of example code on like how to run it on a Droid setup, how to run it on a Aloha setup, zero shot, also fine tuning examples for various robots, things like that. We try to set it up to be really user friendly and easy to use. So give it a try. So we included Pi 5 maybe last month or so. A lot of people seem to like it and think it's improved a lot over Pi 0. So in general, a lot of the process of open sourcing is we really want to learn, where is it not working. And so I think one thing that's really valuable is folks trying it and sharing feedback and things like that. Yep. Cool. So to wrap up here, I want to talk a little bit about some of the lessons that I would say I've learned along the way in doing these projects and the works I talked about. I think one of the really key ones that I didn't fully appreciate until we were operating at a certain scale is the importance of this like really high signal eval, right? So what that means is like diversity in the eval across like not just the quantity but also the diversity of the scenes and these like lower variance eval metrics. So for example, like in Pi 5, we some of our first experiments looking at like, okay, how does performance vary across with like different number of training environments. Some of the early experiments there, like, were really noisy. We were not getting a clear signal of like things that we thought reasonably should help like that. As we added more training environments, it wasn't getting better. And then what we realized is like, well, those first evals we were just doing in our own like testing was like, okay, we were just evaluating it on one unseen environment. And turns out that that's just like not enough, especially when you're trying to probe generalization. It's just not enough to test on like one unseen thing. So it's only when we were testing like across like, like order 10 unseen kitchens and bedrooms, that's when you get the like really clear scaling plot. So it's almost like as you scale data and try and see generalization, you kind of need to scale your eval to a similar extent to actually then be able to see it. Same goes for performance as well, not just generalization, right? Telling the difference between like a 95% and a 90% policy is much harder than telling the difference between like a 40% and an 80% policy. And so you need a lot more quantitative evals and really high quality evals to discern those things. And finally, metrics, right? So like, for a long time, a lot of people just report binary success rate. Metrics like task progress, right? Like how many of the items did you get through just tend to be lower variance and give better signal. So there's been a lot of work that goes into like making eval good and informative. The other bit here, is yeah, especially when it comes to post-training data, the quality really matters, right? So like, for example, in these like folding scenarios, there's a lot of data that's in pre-training, but then when you post-train and you want it to work really well, like really narrowing on potentially a very small set of like high quality data is really quite important. So like when it comes to post-training, like quality is key. Last things we can also do, or it's really important to actually minimize some of the like places where you see train test mismatch, right? So like one of the cases where that's often the case with the robot policies is like inference latency, right? So if you're like running a synchronous policy, um, and you pause each time you run policy inference, well, suddenly that introduces a dynamics mismatch from how your teleoperated data was collected. And so works like the real-time action checking look to basically, effectively run policy synchronously and kind of close that gap. And it ends up being important to do some of these like really fine-grained tasks. Cool. And there's one more, which is so, just important of good infra, right? Like there's a lot of places where there's a lot of little things that can trip you up in the process of like testing and collecting data and evaluating policies on these sorts of systems. Like in this robot station, the camera was bumped around and moved a lot and impacted eval results. So things like automated checks that look for like camera consistency, a lot of like tooling that shows us what's actually going into the policy. Like, on the bottom is maybe what you might see in a video, but when we look at it, we see like, okay, every little thing is logged in the video, so we understand exactly what is going into the model. Just general operating procedures around like scheduling and having consistent people train to do certain evals. There's a lot of operational things and infrastructure things that actually make doing the research here a lot easier. A lot of open questions and things still to do. This question of how do you go from policies that are like 80% to closer to 100%, that sort of production level of speed and performance, I think is very much an open research question. Um, you know, we hope and anticipate that at some point in the future, there's going to be a lot of robots deployed in the world doing different tasks, and there's going to be a lot of that data. And is there a way to learn from it? Is there a way to get really high performance? This is, I think, a really core open question. The next one here is, sorry, my the okay, yeah. Sorry. So yeah, the next one here is around scaling data collection and kind of taking things to the next level of scale. And I think there's a lot of open questions around like what is the right way to scale, right? So for example, if we were getting similar performance to in-domain performance at 100 environments, does it make sense to scale to 200? Or if you're going to scale to 200 environments of data collect, what types of environments should those be? I think as we're getting to the point where like this sort of base recipe kind of works, and then now there's a lot of open questions on scaling, like thinking really carefully about what to scale and how to do so is kind of top of mind. And I think I touched on this a little bit, but basically like metrics and evals at the frontier of your model capabilities are pretty important to determining this, right? Like understanding and effectively measuring what are the things that my model is good at and what's it bad at is kind of key to informing what data you should be collecting next. But doing that is not easy. It's an open research question of like, how do you take a robot that can do a lot of things and really effectively find the places where it's struggling? And I think there's also, algorithmic questions around action representations that are still left to explore, right? Like, are there ways that, you can imagine certain action representations are much more aligned with what is there in VLM pre-training. Maybe you can inherit that knowledge better, right? Things like if you could have your action just be some sort of text, or if it's like a pixel trajectory, maybe that's more aligned with the way these VLMs are pre-trained, but then maybe you lose some dexterity, right? So I think that's one area where there's like a lot of open questions, like what's the right balance to keep your dexterity and full controllability, but best retain VLM knowledge. Cool. With that, I want to leave a little bit of time to answer any audience questions, but thanks.
Thank you so much. This is a super interesting talk. Yeah, and please, audience, both on Zoom in person, really ask questions for the time that we have remaining. There's one that just popped up on Zoom that I'll read out here. It is, what are your thoughts on Dyna's Tau folding policies? Do you think it shows a general recipe for getting policies to production level?
Mhm. Yeah, I mean, I think they've definitely shown some really cool stuff, where, you like taking the approach of like, let's take a task and see what it takes to get it to sort of deployment level, right? And I think with that sort of approach, I mean, I think it makes a lot of sense. I think it really depends a lot on how scoped a task is, right? Like, I guess the way I would look at it is, you know, there's some underlying capabilities that like the base models have, and like can do a space of things really well. Like, so like, the models today can do a bigger space of things when you fine tune them than they could a year ago, right? And probably a year from now, they're going to be able to do a much larger space of things than they can do today. So at any point along that trajectory, you know, it can feasibly make sense to say, okay, you see, there's some task that falls within the bubble of like current model capabilities. Let me try and like specialize on it and deploy on it. Um, and then, ideally, maybe if you have a recipe that can learn from that deployment data, then it's really great, right? Because then you can get like, you can learn from your eval, you can get a really high performance policy. So I think the recipe makes sense. It's really a question of like, how do you trade off between that and the underlying generality, right? So for example, if you deploy a policy in a very narrow context, how
Mhm.
much would that eval data and deployment data coming back in really improve the general capabilities of your base model? Maybe not as much as if you deployed in a slightly more general context. Do you see what I mean? So it's like there's a trade-off of like you want that underlying bubble to grow, and then like
Mhm.
you want to kind of slowly deploy and bring in some eval data, but it's really important that that base model keeps getting more and more general. And I don't think the base models are really at the point yet where you can say like, oh, they're general enough that you can just do everything you would want to deploy for. Does that
Yeah,
hopefully that sort of answers the question?
I think so. Johnny, I'll let you chime in. Yes, he said, yeah, fantastic. Thank you. Edward, I saw you noted you had a question.
Yeah. Yeah. Hey, Suraj. Nice talk. I guess my question is more high level. Just I wanted to see what your thoughts are on basically, training these specialist BC policies on a bunch of action data
Mhm.
versus like some I don't know, big company that's just focused on generic sequence modeling, let's say OpenAI or Google, and they just want
Mhm.
to do like video prediction, LLMs and whatever. And then
Mhm.
eventually, like, in 5 to 10 years, they'll just like try to apply that model to robots. So I just wanted to
Mhm.
see like how far do you think you can push just like training a giant BC policy? If you
Yeah.
think like there's a lot of room for improvement there over some like very general modeling approach.
Yeah. I think this is a great question. I think it goes to, I guess, what all should be included as part of a general modeling approach, right? So, our of course there's text prediction, but if you look at a generally intelligent system, like
Mhm.
is taking actions in the world and manifesting real change in the physical world part of
Mhm.
of a general training recipe for intelligent systems. And I think there's an argument that it is that potentially even if you're building VLMs or world models that you know meaningful intentional action data actually can be key to actually making those other parts better as well, right? Like action is part of the mix with like vision and language, that I think all kind of fall under the umbrella of intelligence. So I guess the bigger question is that I don't view them as that distinct necessarily. Now, more practically, when you're actually building a system, you kind of want to make the most of, take the best of both, right? So you obviously want to take the VLM that's going to give you the best visual and language reasoning capabilities, and also pair it with, the action data that's going to let you have the most robust and dexterous policies. Right now, I don't think that the tasks that you use in like the general pre-training necessarily afford like really dexterous manipulation, right? So it's not clear that just that can enable these really dexterous tasks. I think you'll always need both, right? You'll want to inherit like general vision language understanding, but I think you'll always need robot data to get these like fine-grained manipulation tasks to work really well.
Awesome. Great. Going through questions of the chat. Next one, do you have any interest or see any hope for neurosymbolic methods instead of large VLAs, VLMs for controller prediction for better generalization in very data constrained regimes?
Hmm.
So yeah, thoughts on if there's any role in neural symbolic
I mean, to be
methods.
honest, I wouldn't say I'm an expert in that space. I mean, I think I would really view it as like, I think the architectures and systems that are used in vision and language tend to be
Mhm.
quite general. And I think, ones that can scale with data are important. I think that's been kind of the story of we've seen for a while. And
Mhm.
probably those architectures and systems in terms of like the actual just core like neural network architecture don't necessarily need to be that different for robotics
Mhm.
than they do for vision and language. So sort of my gut reaction is that whatever is working best in kind of modeling generally is likely also a good candidate of what to use in robotics. Now, I think there's a few places where there are special constraints in robotics, things like inference time, which is where maybe this idea of like a system one, system two, where like one of them is maybe more like a classic VLM, but then one
Mhm.
of them is a much smaller model. But yeah, I mean, I think as far as neurosymbolic methods specifically, I would probably see, if there is progress there that, can give sort of leaps and bounds in vision and language understanding, I would expect that it would also help in robotics. But I don't have a lot of experience of like trying these things in the VLA context.
Yeah. Awesome. Um, Thanks. Let me ask a question of my own as
Mhm.
well. I'm curious. No, but imagine at the scale of data that you're talking about, correct me if I'm wrong, but training and evaluating models can be quite expensive and in terms of money, of course, but even probably more time
Mhm.
too. And I'm curious as you're thinking of I mean, both pushing the capabilities that you can do, but also scaling up data and all everything that comes up with that. How do you and the team choose what the most valuable experiments to run or new training recipes to try are out of, I'd imagine there's an almost infinite number of things that you can try, right? But you need to kind of narrow that down into the
Yeah.
handful of most promising
Yeah, I
capabilities.
think I think it's a great question. And it's like, basically like how do we do research here generally? I mean, I think one one thing I will say is like there is still very much a main thread that I think we're all quite grounded towards, which is that like
Mhm.
even more exploratory research
Mhm.
ultimately is towards the vision of like one model that can do,
Mhm.
any robot, any place, any task, right? So at least I think that sort of grounds things a little bit. And as for like individual ideas, you're right that right there is not infinite resources, and so there is like almost like a sort of bubble up type approach, right? Of like any idea, for example, can probably at the very beginning be tested in a very small sim, and then can be tested in maybe a bigger sim, and then it can be tested in like a narrow real world task and say, okay, it's like as good as as good as the previous thing. And then like you basically, I think, increase the scale of data and model and people working on it as like it gets de-risked at larger and larger scale levels, um,
Awesome.
in a sort of iterative way. I think, um, and yeah, I guess my sense is it's probably there's probably a similar question too of how does research on an LLM research VLMs as well, right? That probably not some huge training run isn't being done for every idea, that there's some sort of like bubble up approach.
Awesome. Great. And there are a few more questions. I think there are two more. See if we can get through these, and that'll bring us right about on time for the end of this.
Cool.
One question: what are some of the best infrastructural tools that you've developed that have really accelerated robot research? And I know you hinted at that towards the end. Perhaps talking about no concrete kind of tools
Yeah,
that.
yeah. I mean, just think I think the two big ones that I personally interact with most are
Mhm.
data and eval visibility, right? The ability to like really look at
Hmm.
and understand your data,
Thì tôi ăn đi.
understand its associated annotations, very quickly. Like we have a lot of like what I show is just
Mhm.
a small fraction of our dashboards. There's a
Yeah.
lot of dashboards, right? That go for looking at data, measuring it, looking at like,
Mhm.
okay, on this task, we had data from these places. this
Mhm.
distribution of speeds, right? Because
Mhm.
like a lot, you often, especially for postering, you'll want to pick out like what is the high quality data. So there's like
Mhm.
tons of these sorts of dashboards that really enable understanding the data and like what is good data, who's collecting the task really well, things like that. And
Mhm.
then I think the same goes for eval as well, which is, one, the ability to put in large scale evals that then get run on, 10 mock homes or something is quite useful. And also like the video I showed where during an eval, there's some very clear logging of like what is going into the model. Like you can see the tokenized, everything like full visibility, right? Because like often, I mean, even, despite whatever infrastructure there, bugs happen all the time, right? And like, your policy is not working the way you expect it to. And a lot of those tools give good visibility to like debug that.
Awesome. And the last question we'll end with, have you explored leveraging video models and world models as the backbone for action expert policies instead of a VLM or in combination with fine-tuning of VLM?
Yeah, I think there's folks working on all sorts of areas like that. You're just generally researching
Hmm.
um, in kind of all these sort of exploratory directions of like, you know,
Hmm.
what sorts of data can you use, what sorts of models we can use. So we're kind of actively exploring everything.
Awesome.
You know.
Great. With that, let's all thank Suraj one more time. That was again really, really awesome talk. Thank you again for engaging with discussions, and I'm sure we took a lot out of that.
Thanks.
Thank you.
Awesome. Thank you. And I know there are some. So
Yeah, I have a few chats here, so I think there's a different Zoom link on each.
fantastic,
Yeah, so I'll
fantastic,
join. Cool. Yeah, thanks for having me, Zach.
awesome. Hey, thank you again, Suraj. That was awesome.